But tonight we're going to introduce you to a brand new family of functions, and that family is called a group of power functions. And so our first question is, what in the world is a power function? Well, first of all, the general form of a power function is pretty simple. And we're going to limit ourselves to, one single term here tonight. So the general form is y equals a times x raised to the b power. Now when you look at that general form, both a and b are what we call constants. A constant is, just a fancy name for something that's, simply a number. So a and b are going to be real numbers. Now they may be whole numbers, like 2, 3, 4, or they may be fractions, they may be negative. They're going to get pretty obnoxious at times today. And of course x itself is still the variable that we've always known it to be. So, some examples might be, they might say f of x equals 4x squared. That's a power function, and that's something that we've already seen a lot. It happens to be quadratic. They might say something like, g of x equals, 6x to the fifth power. So a is going to be a number like 6, b will be some number like 5. But we're also going to see a lot of feisty examples, something like, maybe they said f of x is really 1/5 x to the negative 0.2 power. So obviously that's a lot uglier. Here's your a value of 1/5 and your b value of negative 0.2. But as long as those are real valued numbers, it's a power function. So for our first slide tonight, I just want you to go through the 4 examples, and I've tried to kind of jumble them up and rewrite them in a creative way. And I want you to try to decide, are the equations really power functions, And then if it is, I want you to place it in the form of y equals a times x to the b power, if it's not already in such a form. Now, as I look at the first example, I think this is a classic power function. So I'm going to say a big old emphatic yes. Yes, that's a power function. It fits perfectly. Your a value is a 5. Your b value is a 3. That's a great power function. Now, when I get to the second one, that's a very emphatic no. There is no power, plus we have this extraneous second term right there. So this is actually a linear function, and it is not a power function because of the -4. When I get to the third one, it's a little more well disguised. But what I'm going to do is I want to rewrite it. I'm going to say y equals 1/4 times x. What would the power be? Yeah, the power is going to be 1/3. Let's see if the 3, my 3 is not showing. There it goes. Okay, so it is a power function. And my a value just happens to be 1/4. My b value happens to be 1/3. And that's how it is a power function. On the last one, again, let's be a little creative here. Let's see if we could rewrite it. I'm going to say 10 times x to the negative 2 power. So I just wanted to move that x from the denominator to the numerator. And I would say, yes, this is a power function because the a value is a nice, well-behaved 10. The b value is a little feisty because it's negative, but it's still, a nice number, negative 2. And so those are 4 good examples of trying to identify a power function. The next thing that I want to go over is that the common theme here, that power functions, and I like to abbreviate power there, power functions have many common characteristics. Let's see if I can spell this correctly. Many common characteristics. And our goal right now in the next few minutes is to just kind of go over some of the key characteristics that they do share in common. Alright, so the key characteristics here. So we're considering the general form, y equals a times x to the b power, and then want to know, well, what's the y-intercept of a power function as long as b is greater than 0? So basically, what I'm thinking is, b's got to be some kind of a positive number, and when you think about a function crossing the y-axis, whether it's right here, or it crosses here, or even down below, the one thing that all 5 of these red dots have in common is that the x values are 0. And so as soon as they said y-intercept, I want you to start thinking x value has to be 0. So I'm going to go ahead and I'm going to substitute a 0 in for x and see what happens. So I get y equals a times 0 raised to the b power. And what you'll notice is that 0 raised to the b power really 0 raised to any power in the world is simply 0, and of course a times 0 is 0. So what we just discovered is that the y-intercept for every power function will always be y equals 0. Alright, next question here. What's true about the y-intercept if b's less than 0? Alright, so when they said less than 0, they were trying to say negative. So let's think of something like y equals ax to the maybe negative 2 power, or negative 3 or negative 5 or negative anything. The first thing you would do to that function is rewrite it so that the x was on the bottom, wouldn't you? So in this particular case, if I substituted a 0 in for x now, and again, it doesn't matter what the exponent is. It could be a squared, a cubed, a 4th power, a 5th power. It could be a 20th power. I don't care. You're going to get a divided by 0. And what that is that means the function is undefined. And we really haven't talked about this yet, but what that means is graphically there's going to be something called a vertical asymptote. We've maybe seen a couple of those just randomly in class, but so what's going to happen is your graph, when you go to graph it, there's going to be a vertical asymptote right down the middle of it, and that's going to greatly affect your graph. So for the most part, we're going to stick with positive b values, but not always. Alright, so we're going to study some more characteristics, and the characteristics and the behavior of the power function is highly dependent on its exponent. Okay, and specifically I want to know, well, if it's an odd positive exponent versus an even positive exponent, certain things are going to happen all the time. So what I want you to do is I want you to grab your calculator, and I want you can use a standard viewing window. You can just go zoom standard, and I want you to neatly sketch the 4 following functions in your notebook. I want to see x squared, I want to see x cubed, x to the 4th, and x to the 5th. So these are all power functions. They all have a value of 1, and their b value increases gradually. So go ahead and sketch those as carefully as you can, and then come on back, see if both you and I have the same picture, and we'll try to put on our detective hats and see what they have in common. Okay, so just to help illustrate a point, I did the even-powered power functions, the x squared and the x to the 4th. I did those in red here, as you can see. And then I did the odd-powered functions, like the x cubed and the x to the 5th. I did those in blue. And basically, you'll see my two red graphs are almost identical. It's just x to the 4th is a little bit tighter. It just increases at a faster rate because of the power being bigger. Similarly speaking, the x cubed here and the x to the 5th are very, very similar. Again, the only difference being x to the 5th is a little bit tighter, more narrow, just because the bigger exponent forced the graph to increase at a faster rate. So what do we have in common here? When you look at an even-powered function, such as x squared or x to the 4th, both endpoints go in the same direction. Both endpoints go in the same direction. What we're referring to there is that the endpoints are the arrows here at the end. In this case, they're both heading towards positive infinity. And again, on x to the 4th, both endpoints are heading towards positive infinity. However, when you looked at the odd functions, x cubed and x to the 5th, the endpoints are heading in opposite directions. One endpoint's heading towards negative infinity, and the other endpoint is heading towards positive infinity. And that's an important characteristic to know. So we've got negative infinity, positive infinity, negative infinity, positive infinity. Now, interestingly enough, what if I wanted to negate these functions? If I negated x squared, it would flip it over. Okay? If I negated x cubed, it would turn it upside down, kind of like this. If I negated x to the 4th, it would flip it upside down. If I negated x to the 5th, again, it would kind of turn it upside down, so to speak. So here's a great multiple choice question, and we're going to answer it pretty quickly. They said, well, which of the following power functions is shown in the graph below? And of course, you could grab your calculator and you could type in each individual function until you got a picture that kind of looked just like this one. But I think it's easier than that, guys. I think it really do. Are there any of the 4 choices that you think you can eliminate right away? The first thing I noticed is that both endpoints are heading in the same direction. So what that means is it's got to be an even-powered function. That was my first decision. So I crossed off this guy because of the 9, and I crossed off this guy because of the 7. The second thing that I noticed was that it was entirely below the x-axis. So I was assuming that they negated the leading coefficient, and that's why I jumped on number 2. I saw the negative in front of the 3 right there. That forced it to be upside down. If I had graphed 6x to the 8th, it would be more upright here in the first and second quadrants as opposed to the third and the fourth quadrant. Now that we got a pretty good feel of what a power function is and how it tends to behave, and that we know the y-intercepts are 0, 0. We know that if it's even, both endpoints are going to finish in the same direction. If it's odd, the endpoints finish in the opposite direction, so on and so on. Here's this is the wordiest slide of the night by far, but I want you to hang in there, take careful, meticulous notes, and I'm sure it'll deepen your understanding as we move forward. So power functions are commonly used to fit data. Now, when we talk about fitting data, we're referring to a scatter plot through the process of a power regression. So that's really our big theme tonight. Everything we've done up to this point is simply considered warm-up. So we're talking about power regression. So we are going to use a ton of calculator from this point forward. So really, really make sure that that calculator is in front of you, it's available, and that you're ready to be able to push the same buttons I'm about to push. I'm going to take the best pictures I can so you can follow along. So I'm picturing, when I say scatter plot, we're thinking, maybe I've got a series of dots that maybe, they don't go in a linear pattern. Maybe they kind of arc. And you'll notice that maybe the best fit curve, not best fit line, the best fit curve goes like that. And that's what we're going to look at tonight. Now the procedure is identical to that of a linear regression, which we're very good at. We've proven that several times on tests and quizzes, except that we'll fill the data with an equation in the form of y equals ax to the b power instead of y equals ax plus b. So, y equals ax plus b or mx plus b. This one was linear. We're not worried about that one. We're going to do a power regression tonight. Now, power regressions are most commonly used in situations where data must include the point 0, 0. As we've already tried to prove tonight that the y-intercept is always at 0. In other words, the two variables must be 0 at the same exact time. So here is one of the big bears that we're going to tackle tonight. We're going to use a ton of calculator. There's going to be very little on our paper by the time we all said and done. But of course, what is on our paper is extremely important. So here's the question. We're talking about Kirk here. Kirk's measuring the height of a germinating corn plant as a function of the days since they first broke the soil for his 8th grade science project fair project. He measured the following data. So days since germination, 2 days, 5 days, 14, 20, 25 days, 35 days, and 42 days since germination, and then the average plant height on those days. So after 2 days, the average height was 6.3, the average height was 9.1, the average height was 15.8, etc., etc. Now when we see these tables, the first row is always going to be your x values, the second row is always going to be your y values. Now what we do as far as our calculator goes is we're going to go to our list and we're going to edit, and the first row is going to be L1 and that second row is going to be L2. So let's go ahead, let's fire up those calculators, let's enter all of the data into the appropriate lists. Alright, so here we go. So I just I took the time and I put all of these rascals in L1, all these rascals in L2, and just to recall how to get there, there is a stat button right there just below the delete button. If you hit stat and you want to go to choice number 1, edit, and it'll take you to these lists. Now, if you already have numbers sitting in your L1 and your L2, you want to highlight the L1 and hit the clear button. You do not want to choose delete. If you accidentally hit delete, it's not the end of the world, but just bring your calculator to me tomorrow and I'll make sure I fix it. And so you can clear out those ones and then you can go down, just be very careful. And even now, when I was doing this, I was very paranoid to make sure I typed in everything correctly. I wanted to make sure that I didn't miss a decimal. I wanted to make sure that I didn't accidentally screw up one of the numbers by just trying to go too fast. Now once you get all the data entered into the list, you can go back, hit the stat button again. It's going to take you to the edit menu, but you want to go over to the calc menu. Go over to calc. Now we used to use choice 4 right here, linear regression, but we're done with linear regression. We're moving beyond that. And power can't be seen yet. You want to scroll down the list, keep scrolling until you get the choice alpha A. And there's your abbreviation, PWR regression. Choose that one. When I did choose that one, my calculator said my A value is 4.341687522. But anyway, they just went nearest 100th. So that's 2 decimal places. So let's say my A value is 4.34. and that's going to be times x. The parentheses around a are optional, but I do encourage you to use them. And I'm going to go 0.49 on the exponent. 0.49 on the exponent up there. So there's my equation. Now be very careful and neat. I want to make sure that your exponents actually look like exponents. I want them to be the appropriate size and in the appropriate position. Okay, next one. Use your model or your equation, whatever you want to call it, to interpolate. Now interpolate means we're going to use a number that falls within the endpoints right there. And you notice that 30 does kind of fall in there roughly. So we can kind of roughly predict using the eyeball test that the answer should be somewhat near 22-ish if this is correct. What I'm going to do is I'm going to substitute the 30 and I'm going to show my substitution. Now that is an x value. So I'm going to say y equals 4.34 times 30 raised to the 0.49 power. And I'm just going to plug it into my calculator and see what we get. Now if I round my answer to the nearest tenth of a centimeter, I'm going to get 22 point, oh boy. Now the rounding is interesting here because it's 22.97. So my 22.97 is going to round up to 23.0 centimeters. And judging by my table, that's a very realistic answer that could have fit in there. All right, next thing. Now we're going to extrapolate. That just means we're using a number that's outside, it's beyond the edge of my table, so we're kind of going beyond our normal realm here. And let's see, I need to substitute the 60 in for x. So I'm going to show my substitution. Y equals 4.34 times 60 raised to the 0.49 power. Again, I'm going to throw up my calculator. Again, if we round to the nearest tenth, I'm going to get an average height of 32.3. It was actually 32.26. And again, I'm going to throw centimeters on there. All right. Last but not least, they want to know, hey, for simplicity, Kirk concluded that the average plant height could be modeled by this equation right here. And we want to know, is he justified? Is that even close to the equation that we had? Well, I think it is pretty close because if you want to use a radical, that means your exponent is really 1/2. So is this, somewhat close to the exponent we were using? I would say yes. So I'm going to give Kirk the thumbs up here. I'm going to say that for simplicity purposes, that his model is very accurate and very, very close to the regression that we came up with. All right. Well, I'm going to throw a few more bear traps at you here and see if we can keep you on your toes. Now, they said in the accompanying table shows the number of new cases reported by the Nassau and Suffolk County Police Crime Stoppers program for the years 2000 through 2002. So we had 457 cases, 369, 353, yada, yada. Now, here's important. This is important, and this tricked us a little bit the last time we did linear regressions about a month ago. They said, I want to let x equal 1 represent 2000. So the first thing I'm going to do is I'm going to say, you know what? I'm going to say that's a 1. I'm going to say this is a 2. I'm going to say this is really a 3. So when I go to my calculator and I start to put things in L1, I'm going to use 1, 2, and 3, not 2000, not 2001, not 2002. All right, and then Y represents the new cases. So, here's my L1, here's my L2. I'm going to get ready to go plug them in. And let's round. We are doing a power regression. We're going to round all of our coefficients to the nearest thousandth. That means we're looking at, let's see, tens, hundreds. That's 3 decimal places that we're going to need. And, of course, we don't want to get careless and lose any points because of silly decimal places. All right, my calculator is showing me, and of course I had to highlight the L1 and clear it. I had to highlight the L2 and clear it out. Did not want to delete it. My model is coming up with 451 point, I'm going to go 431. So it was actually 4309. And I'm going to just put that in parentheses just for clarity. And then I've got my x, and the power on my x is going to be a negative 0.243. Again, it was originally 2429, but I'm going to round up to 3. So there's my model. And then the next thing they want me to do is to use this equation to estimate the number of new cases for the year 2007. Now, if you see the pattern here, 2007 is equivalent to x equals 8. Just because, 2002 was really a 3, so on and so forth. So what I'm going to do is I'm going to go ahead and I'm going to substitute an 8. Again, this step right here is very necessary. We need to show that, where we're substituting it and for what variable. And now I'm just going to be really careful and plug it into my calculator. Now, they did ask me to round it to the nearest whole number, so as I carefully entered it into my calculator, I got 272.358, yada, yada. That's going to round to 272 new cases. And the good news is we do have a good trend here. The number of cases is dropping. And so that's a good thing, I guess. Yes. All right, ladies and gentlemen, it is your time to shine. We're going to let you guys take over on this one. Just going to kind of set you up here. We do have water draining from, whoa, don't want to do that. Water is draining from a tank maintained by the Yorkville Fire Department. Students measured the depth of the water in 15-second intervals. And I tell you what, pay attention to your units, ladies and gentlemen. We do have ourselves one of the sneakier bear traps later on in this problem. So the first thing they want you to do is they want you to come up with a power regression. So grab that calculator. Let's get everything into L1. Let's get everything into L2. Be very, very careful to make sure all decimals are correct. We're going to round everything to the nearest 10,000th. So that's actually, we're looking for 4 decimal places on both our A value and our B value. And then you're going to use that equation to predict the depth of the water after 2 minutes. Now, I hate to ruin the surprise, but I can't resist. Now, keep in mind, X was measured in seconds. So we've got to make sure we figure out 2 minutes is equivalent to how many seconds. And that'll be the number that you substitute into your equation. So here's what I need from you guys. And we're going to check your notebooks tomorrow. First of all, we're going to write that power regression, rounding everything to 4 decimals. And then what you're going to do is you're going to figure out what to substitute and into what variable. And we're going to figure out what is the depth after 2 minutes. So good luck, and we'll see you tomorrow.